I'm going to keep my introduction very brief because I'm sure you much rather listen to me giving his talk. It gives me great pleasure to welcome Yves to this occasion. Yves is the Richard Snape Professor of Economics in Monash University. He's an amazingly prolific and very influential researcher, diverse range of interests, stretching from, of course, his work on social networks, for which he's probably most well known, but he's also written extensively on, amongst other areas, urban economics, segregation, etc. Without further ado, I will request Yves to give his talk.
Thank you.
And Yves would like to he'll speak for about 50 minutes. He would like to, he'll take questions at the end of his talk. Of course, if you have any clarificatory questions, please ask him, and he'll decide whether it's clarificatory or not.
Okay, so first, thank you for the invitation. It's nice. It's my first time in New Delhi, so it's nice to be here in India, and I will stay the whole week to visit the country. So let me present the idea. So I will present basically the main idea about peer and network effect. Then I will present in more detail a paper, and then at the end I will open up why network is important. And what is interesting for this conference is that I'm going to do theory, econometrics, and structural estimation and data. So it's nice you will see a different aspect of the network. So basically, there's a huge literature on peer effect. I think more than 1,000 papers, where they try to understand how peers have an effect on any outcome you can think of. Of course, I've just listed some of them: education, crime, risky behavior, obesity, drugs consumption, and so forth. So there's a lot of paper about that. And over the years, over the last 20 years, my understanding of the literature is that they've been obsessed with improving the identification of estimating the peer effect. In other words, trying to find RCT, random allocation, shocks, and that's the way the literature have been proceeding. And this is the equation that everybody is testing. So on the left-hand side, you have an outcome for individual I or agent I in group G as a function of the average outcome of some group, right? That's what people are doing. And basically, I could be, the outcome could be whatever you want, test score, could be crime activity, and so forth. And the group at the peer effect level could be the neighborhood, could be the classroom, could be the school. And you want to see if, on average, people in my school are performing well. Am I performing well? And as you understand, it's very difficult to identify. So there's huge literature trying to find a way to identify this peer effect. This is the lambda that you want to estimate. That's the peer effect literature. Now, what about the network effect? Well, you see, it's the same equation, but the main difference is that now, instead of defining a group in a very abstract way, now it's a much more precise way of defining. So Gij is going to go to 1 if there's a link between the two agents. Could be friendship, could be a patent, could be an R&D relation, whatever. But so it's a much more precise relationship, and I divide by the average links of each individual, what I call the degree, right? So this is a two equation, and you say, okay, what do we learn from switching from here to here? There's a lot of advantage. For example, the reflection problem doesn't exist. There's a lot of advantage, but I want to go more from the policy point of view. What do we learn from that? And just to understand, when you do peer effect, you make big assumption. You assume, for example, think about the classroom, that every person is affected the same way. So I am in a classroom. I'm assuming that I'm interacting with everybody in my classroom. I look at the neighborhood. and there's 2,000 people, I'm assuming I'm interacting with everybody. So it's a very strong assumption, and the boundary is not clear. Are we going to take, if I do empirical work, I'm going to take the classroom, the school, the neighborhood. You know, you have to make decisions there depending on the data. So when you do network, of course, what you do is that you take the smallest unit of analysis is a one-to-one, the diode relationship. So I'm going to look relation 2 by 2, the Gij in my equation, right? And I want to see how friends or very direct interaction will affect me. And one important aspect of this talk is that when I go to network, I can do targeting policy because I know exactly the structure of the networks, and clearly in terms of policy, I can go further about that. So that's the idea. And now, there's two main questions for this talk, which I think are very important. The first one, it's fine to have a linear mean model, the one I showed you before, but do we have any theory? You know, it's fine to do some empirical work, but is there any model that can microphone the linear mean model? And actually, what you see is that there's some paper about that, right? But what it's found is that there's more than one model. There's two models, and of course, depending on the model and the function, the policy application will be very different. So the first thing, we need to understand that. But the second part, which is the main contribution, I think, of the paper I will present today, is that we are making huge assumption, linear in mean. You know, if I'm a criminal, do I care about the average of the group? Maybe I care only about the gang leader. If I take risky behavior, I want to smoke drugs, do I care about the average or do I care about the least guy or the highest guy? So what is the answer about that? And what you see is there is some paper with no theories that try to find, oh, let's take the max or the mean or both. But we don't know exactly what's important. And why it's important, if I want to implement a policy, I need to know what do you care about. So if I want to do in a inner city neighborhood in the US and improve the poverty, I need to know, like the black kids, who they care about. Do they care about their father, about the top guy in the neighborhood or the worst guy? I need to know that. And it's not clear in the literature who is the person you care about. So I have this paper that I want to present today. It's called Toward a General Theory of Peer Effect, which is joined with Vincent Boucher from Laval, Michel Randall from Monash, and Philippe Houchel from Belgium. Basically, we're going to answer these two questions. The first one, which model exactly microphone the linear mean model, and we're going to develop a very general model where the Lee model is a particular case. That's the theory part. But then we go further. Of course, I'm going to show you first that there's two models, and only two models, that can derive the Lee model as a first order condition. Okay? And it's called the spillover effect model and the conformist model. And these two models have, even though they have the same first order condition, the policy applications are very different because the utility function and the welfare are very different. So you will see that the first thing to see, if you want to run a peer effect model, you need to know which theory microphone the result. That's the first question. The second one, which is the most important part of the paper, we relax the linear mean model. We develop a very general model, right? And the mean or the linear is just a particular case of this model. And of course, we're going to develop the policy application of the model. Now, this is the only theory, but then you have to go to the data. You know, if you do theory, you're not going to convince anybody doing empirical work. So we say, let's structurally estimate the model, and you can only structurally estimate it because it's non-linear, so you cannot do reduced form estimation, so you have to structurally estimate the model. And what we show is that for some, we're going to take 10 activities, you will see, and for some activity, for example, GPA, education, social club, self-esteem, exercise, the spillover effect matter, and I will explain what does it mean, but for other activity, the conformism model matter. Now, more importantly, is this part. What I show is that most people don't care about the average. So when I estimate the model, I show that most of the people, for example, in GP, fighting, self-esteem, exercise, so forth, you really care about the top guys. So if you want to study hard, you really care about the guy with the top in your class or in your group, right? And the second question is that for some other activity like trouble behavior and drinking, the least active people are going to matter. And why do we matter? In the last part of the paper, I will do counterfactual policy. I say, imagine I'm a planner and I want to implement a policy of restoring the first best. Well, how much mistake I'm making if I think it's a lean model, the average one, whereas I look at the real model. And the mistakes are huge, really important. So it's a really methodology paper showing you how much we need theory to understand our particular work and how many assumptions people are making, the reduced form people, without knowing it. So they make a huge assumption and they make mistakes. So maybe it's a praise today of theory is not dead. There are no theory, all our students or people on the market that never find a job when you're in theory, but theory matter if you really want to understand the policy implication. And that will be one of the conclusions. So I'm going to do some theory using standard network theory. I hope you're familiar with that, but it's not very complicated. So if you think about a network, everything could be defined in terms of a graph theory. So I will define what I call an adjacency matrix. It just keeps track who is in link with whom, right? So if you look at this network, right, I say 1 is not in contact with himself, but is in contact with 2 and 3, as you can see here. 2 is in contact only with 1, and 3 with 1, right? Then, because, as you remember, I'm going to look at the linear in mean, I need to look at the average. I'm going to define this row normalized matrix, which is just the same matrix, but I divide by the total number of links. So I divide by 2 here, and I define by 1 and 1. And this is the stochastic matrix, the sum of the row equal to 1. Nice property, largest eigenvalue is 1, so I mean the standard property. So basically, this is the matrix I'm taking care of. From the theory point of view, I can do directed network if you want. I can do weighted network. It doesn't matter. Everything goes through. But I just use this one as the main example. OK, so this is, I showed you before, the linear and mean model from the network perspective. So my outcome is a function of my characteristics, the average outcome of my links, and some error term, right? So can we write down a theory model that finds this equation? So there's actually 2 models, or any combination of these 2 models that you can find. As you can understand, because it's linear and mean, you need to have a model with a linear quadratic utility function. Otherwise, you cannot get the linear and mean. So one of them is called the spillover effect, the spillover model. So when you look at the utility function here, I need to define how much effort I'm going to do. So y is the effort of each agent. And remember, there is 2 parts. The first part is independent on other people. So this is how much effort I'm going to put depending on the alpha I, which are my observable and unobservable characteristics. So for example, I'm going to commit crime depending on my education, of my parent education, of my ability to commit crime, and so forth. Now, the key part is this part, is the interaction with other people. So it's going to depend on my own effort, but also of the average effort of my friends or the people I'm linked to. The more my average effort of my friend put effort, the higher is my utility of committing effort. And in terms of intuition, this θ1 is how much is this strategic complementarity if you want, but it's also called in the empirical literature the social multiplier. Right? So basically, imagine I'm a person, I'm committing some crime because I have an ability and I have characteristics. θ1 will give you how much extra crime you're going to put just because you are connected to someone. So let's say I'm committing 2 crimes, I'm connected to someone, and θ is 0.2, I'm going to double my crime. Okay, so it's a social multiplier. That's the idea. So this is a simple problem. If I solve the Nash equilibrium for any network, so any possible network with n agents, I calculate the best reply function, and you can see that clearly it's a linear and mean model, right? So effort is going to be depending on this one. It's a very simple fixed point theorem to find it. If θ1 or alpha or lambda 1 is less than 1, clearly you have a unique equilibrium where everybody is going to put a positive effort equal to this value. Okay? So that's the first model. But it's a spillover FM model. The more you are connected to people, the more effort you're going to put. Now, there's another model, which is very, very different. And some economics can work on that. It's called the conformist model. So what does it say? First part is like before. But now the second part, you have this -1. What does it mean? It means that each time you deviate from the norm of your friend, this is the average effort, you pay this cost. So it's costly for you not to conform to the group, and theta 2 now is a test for conformity. So the higher is theta 2, the more you want to conform to the people, right? So you see it's a very different model. One, it's a spillover. You spill over from your friends. Here, you don't want to deviate from the average of your friends. But if you write the first order condition, it's the same idea. There is some more parameter. Again, my effort is a function of my characteristics. It's the average of my friend and some error term. Okay? So there is two models, and only two, that can lead to that. Or, of course, any combination of these two models. I'm going to put them together to show you that. But basically, these two models will lead to that. The problem is that, as you will see when I do the policy applications are usually vastly different. So first order condition is behavior, utility is welfare. And the welfare is very different, and I will clearly explain why it's different. Okay? So these are the two models. For example, one policy that I will do, which is the simplest one, as you understand, there is a lot of externality in this model. So the Nash equilibrium is not the first best. Let's have a planner who wants to restore the first best. Well, if you have the spillover model, everybody is putting effort too low compared to the first best, so you subsidize everybody. However, in the conformity, it's not true. You tax some agent, and you subsidize other people. Of course, if my effort is very high, the average is going to be very high, and it's bad for the other people because they're far away from the norm, so you need to tax the guy which are providing a lot of effort and subsidize the other one. And I will be very clear about that. So the policies are totally different. So what I want to do is say, if you want to do a peer effect regression empirically, I'm going to give you a methodology that tells you which model fits the data and which policy you should say. All these peer effect paper indication, they say, give subsidy to everybody. Why? I'm going to show you it's not true. It's wrong, actually, if you do that. Okay, that's the first thing. So what I'm going to do, I'm going to embed these two models together, right? So I'm going to put the spillover and the conformist model in a simple model of cost and benefit. I'm going to solve the first order condition, and this is a general model, linear linear model, but with these two effects. And of course, when lambda 1 goes to 0, you go back to the conformist and so forth. Why I'm doing that? Because now I have a first order condition, and I can test from the data if it is lambda 1 or lambda 2 for each activity. And I will tell you which model match the data using some GMM methodology. Okay? Is that clear? And it's very simple. You solve the Nash equilibrium. Everything is linear. You have to inverse the matrix, and the equilibrium is unique if lambda 1 plus lambda 2 is less than 1. Okay? So that's the first thing. Now, that's the first part of the paper. Second part, which is more important and more original, I think, is say, well, why we are imposing this model? Why can we have a general model? It took us some time to find the right model. I wanted the model with only one parameter, and this parameter could be tested to see which one matters. So I came up with the CS function. So imagine the norm, instead of being the average, it's the CS function. Why it's nice? Well, the nice aspect is that when beta equals 1, you have the linear mean model, right? But when beta go to infinity, you have the max. When beta go to minus infinity, you have the mean. And you can do everything. The good thing I will show you, I can estimate the beta from the data and tell you which matter. So 1 will be my benchmark, and if I go above 1, I'm going to squeeze or skew toward the most active agent. And when beta is less than 1, I'm going to skew towards the least active agent. But I can calculate the exact beta for each activity and tell you which one matters. And then I can do policy. Okay? Now, the only problem, of course, if I take the general model and I solve the first order condition. Of course, now to show existence, especially uniqueness, is much more complicated because the model is not linear anymore, but fortunately we can solve it. Existence is easy because it's just it's a game with supermodularity, so it's easy to solve. Uniqueness takes a lot of time, but we can find it using some contraction mapping theorem. So basically what we show is that take this utility function with a CS norm, assume that the lambda are not too high like before, then for any possible network, there's a unique equilibrium, which is anterior and given by the equation I gave it before. Okay, I'm not getting detail. If you're interested by the proof, it's on the paper. We can show actually something much more general for any norm which have some property. It's increasing and homogeneous degree 1 and some inequality. It's always true also. So we have a general about that just to show it's not only for the series. Okay, so far, I hope you understand. I show you two parts. First part, which model microforms this limb, and let's relax the limb and have a general model, but as you understood, there is one parameter beta that determines which person you matter. It's very important. Do I care about a very large beta, which is the most active guys? Do I care 1, which is the average, or so forth? Okay? Now, I need to go to the data, and I need to explain you what is my structural estimation. I'm going to do very standard GMM. So it's nothing super complicated. The only thing I want to be sure that the model fits the data. So you do GMM and you see how much the fit is good. So basically, I need to estimate these 3 parameters. Lambda 1, which will be the spillover model. Lambda 2, which is a test for conformity. And remember beta, which is a social norm, which part of the one you matter. So here's the equation I want to test. Remember, first order condition. This is the econometric equivalent of the first order condition. The only thing that I have added here, it's a school fixed effect. It's going to be data about kids in the US. School fixed effect to be sure there's no problem. Now, the problem here is that if you estimate this equation by structure estimation, you cannot distinguish lambda 2 from gamma. So I'm going to break that by looking at first isolated individuals, right? Why? Because if you isolated, you don't have the second part of the, by definition, you don't have links, right? So basically, what I'm doing here, I say, let's estimate this model because they don't have any friends, by definition, they're isolated. I can estimate the gamma from here, right? And once I have the gamma, I can estimate the lambda 2 and everything. Now, of course, I'm making an assumption which is strong. I say isolated and non-isolated have the same characteristics given that I control for sorting into schools because I have school fixed effect, right? And of course, what I'm going to do a Robinson check when I will test everything on non-isolated and show you that the results are robust, right? So that's the way you have to break. It's difficult to find another way, but it's relatively clean to do that. I will do a robustness test to be sure that it holds here. So the first thing for estimating gamma, I'm doing GMM on that, and the moment condition is very simple. I'm assuming that the error term and the characteristic of agents are independent, which is exogenous, which is fine, and then I can get the gamma from that. When I've got the gamma, then it's easy. I can get, as you remember, the lambda 2, because I have the gamma now, for GMM again. Then I do from non-isolated one, and the moment condition is similar. Then I need to do the last one. Well, I'm going to do the norm, and assume the norm and the epsilon is independent. And the last one, I'm going to use the slope of the norm to get the last estimation of that. So it's relatively standard you can get on the paper. So with that, I will be able to estimate gamma from here, lambda 1, lambda 2, and beta. And then I minimize this function. You know, it's a weighted function. And then I get my estimation. Okay, so what data I'm going to take? When you do network analysis, there is some data set, Esther Duflo and Banerjee and Arun and Matt Jackson, they have this Indian data set, but it's not very convenient because they have the network, but they don't have that many activities. So there is this standard one that I guess most of people know. It's called the National Longitudinal Survey of the Adolescent Health in the United States. is very nice because it's representative of the US, is all the kids between 14 and 18 years old, right? And what is nice, they have not only the networks of every agent, and it's complete, but they have many, many activities, okay? So I can test it, and more importantly, it's big sample. It's 70,000 people I've got here, representative of the US schools. So I'm going to get, in terms of network, what you ask, what are your best friend, up to 10, and you have to do male and female. And then you have many activities here, and so I can construct the network and I construct the activities. So I'm going to get 70,000 students from 134 schools, representative of the US school. So here's the 10 activity I'm going to take, right? So first activity is the standard one GPA. I want you to remember that the value is between 1 and 4. It will be important when you do policy. So 1 is the lowest grade you can get, and 4 is the highest grade, right? And we're going to do 4 disciplines, and we're going to mix of them. Then we're going to do social club. How many clubs you're going to participate while you're in schools? You know, it's an important point. Self-esteem, which is self-reported. We're going to have an index of self-esteem which is going to go from between 0 and 1 if you have strong and bad. Then you have risky behavior, you know, smoking cigarette, drinking beers, and so forth. Exercise, study effort, fighting, smoking, drinking, trouble behavior, which are standard peer effect. The thing you have to remember is that the more you increase the number, the more you're active in this activity. So here are the sample statistics, and I give you 3 points about that. I don't think you can see. The first thing is that activities are reported consistently across activities. So if you look like, for example, this is a GPE club, you see that age is similar, 15, female fraction 50% similar, Hispanic. So it's very consistent across activity. The second thing is that it's increasing. So the higher is this number, the more you are participating. And the interesting thing is that in the data, 14 to 15% of the people are not isolated. So what does it mean? We have an indirect network. It means that nobody have nominated them, and they have nominated nobody. Okay, that's the idea. So I'm going to show you first the first estimation of which model microphone each activity. That's the first part, okay? And then I will do of course, the estimation of beta. And I'm going to compare the general model when beta equal 1, the model for the spillover only, conformist, and the standard linear mean model reduced form that people are using. Okay? And some good. So this is what you see. I'm not sure you see the number. I will interpret them. But this part is very important. This is a general model where I'm testing lambda 1 against lambda 2. So what you can see is that for GPA, what matters is spillover. They don't conform to the norm of their friend, but they care about how many of their friends are doing study, okay? And so forth. So for clubs, the two models are true. And for self-esteem, it's mostly the spillover. For risky, it's mostly the conformist model. And you can see that this is the objective values that I am minimizing. Remember, for the GMM, this is a function. And you see the fit is very, very good. It's close to 0. And the likelihood ratio is very high. So it's really a good fit from the data. Of course, you have 70,000 people, it's a relatively easy model. So what do we obtain? First, we obtain from the data, actually, each activity have a different model. So when we look at the model here, we see for GPA, self-esteem, and exercise, you care about spillover. That's what you care mostly. So you care how many of your friends are doing some activities, and you look at the average of them. Remember, that's the linear mean model, okay? When you look at risky behavior, study effort, fighting, and drinking, conformity matter. So if your friend smoke or drinks, you want to conform to them. And you understand the difference between conformity and spillover. Spillover, imagine I have 10 friends, right? And on average, it's 10 friends, I don't know, smoke 1 cigarette per day, okay? Now, in the conformist, I want to smoke as close as possible to 1, and the spillover is one thing. Now, imagine now, I find new friend. From 10, I go to 15, right? But this 5 to friend still smoke 1 cigarette. The conformist model doesn't matter. I still want to be one friend, one a day, but the other one change. Because now I am calculate the new average of the number of people. So the more people you are there, the more it's going to change my behavior. So it's a different model in terms of behavior. And I can look at different things. I can look at how much how much difference you have between the reduced form and my model. It's different. So the estimation of the lambda, remember, which is on the use parameter, changed a lot. So 10% different with this one, 30%, 40%, 190%. There's a huge difference in terms of impact of the social multiplier, basically. Okay? So this is the main table. What's happened now if I test beta? Well, what you see is that you never get 1, very, very rarely. So if I look at the GPA, it's spillover a model, and beta is close to infinity, is very large. So I care only about the most active person. So I am in a group of people, like 4 friends. I don't care about the average. I care about the guy who is the best in the group in terms of GP. That's the only one I care about. I don't care about anything else. If I go to clubs, then I am indifferent in terms of model, and I'm slightly above 1. So slightly skewed towards this guy. Now, if I look at self-esteem, not surprisingly, I care only about the person who have a high self-esteem. I don't care about people with low self-esteem. If I look at, I don't know, risky behavior, it's interesting is that I'm below 1. So I care mostly about people who are less risky behavior. I don't like people who take risks, drink a lot, or smoke a lot. I'm below the average, and so forth. And risky is conformism. I want to conform to the guy which is below. Here, I want to have the spillover to the guy which is above 1, and so forth. Okay? Tribal behavior is interesting. You go to the mean. I really want to care in my group of friends about the least tribal people in the group, the least one, and I want to spill over against them. Drinking, I want to conform to them, but I want to look at people who don't drink too much, and so forth. And of course, this methodology depends on the, if I do that for other data set, I will maybe get other results. So it's specific to the US and for this kind of activity. So what do we learn is that the beta is not 1. It's nearly never 1. So people, by estimating the linear mean model in the peer effect literature, are making a huge assumption, which is wrong. People don't care about the average. And so you cannot do a policy if you believe that people care about the average, while in reality they care about the top or the mean or stuff like that. So you make a lot of mistakes, and I will show you in the counterfactual how much mistake you are making. Okay? So as I already say that, it's very rare that beta equal 1. Now, I can show you how much difference in terms of the estimation. You know, it's a big difference here, and so forth. So that's the first part of the paper. So you understand that we have this problem. I show you, remember, to break the estimation, I was assuming that I'm going to look at isolated individual, and you can tell me, I'm not sure the characteristics are the same as non-isolated. Maybe there are different. So what I'm going to do, I say, well, let's forget about which model microphone the data. Look only on the beta. In that case, you don't have any more the problem because you don't have this term anymore. This term disappears. You only care about the beta. You estimate the model on non-isolated individual, and what you obtain, similar things. So the beta, this is what we did before. This is what we do only on non-isolated, and you see the number are very, very close. In this case, beta is not 1. So you show that the results are similar, and we do a lot of things which I don't want to get. I want to speak about ideas today mostly than technicalities. Okay, so now I'm going to do some simple simulations, then I will go to policy, right? So yeah, I'm good in time, I think. Okay. So look, just for you to understand the intuition, I'm going to simulate. So what I'm going to do is that this is in red, the linear in mean model, and I'm looking only at the social norm. So the social norm of people, how many people I care for. So GPE, remember, you care about the most active person, and it's a spillover model. So this is the linear in mean model, which you believe is a wrong model, obviously, and this is a right model. So what do you see? You see two things. you see first that there is all this peak here. Why? Because within each group of people, you only care about the top guys. Here, all of them. So this norm is very different. You don't care about the average of people in your group. You only care about this small peak and the top guys in your school. And the same thing when I look at, I multiply the norm by the lambdas, by the social multiplier, you see how much different this is a linear mean, and this is the general model. So I just want to show you, I'm not doing policy, I just show you how much difference. So if you don't know, for the population you are studying, which social norms they matter, how you can address policy. And I'll show you the mistake you are making. So I can do the same thing for risky behavior. You see that it's close to 1, so it's relatively close. But when I multiply by lambdas, I see some difference. Same thing for self-esteem is, it's shift to the right because beta is quite high, and so forth. Okay, so now, so far I show you it's wrong. Now I need to show you in a policy example why is wrong and how much is wrong. So I'm going to do the simple public economic policy I can do, which is if the Nash equilibrium, which is not the first best, the planner, after he said how much subsidy or tax is going to impose on each person to restore the first best. Okay, so very simple exercise. Welfare. So what you do is that you have a welfare function, which is the sum of utility of every agent in a network. And again, remember, in the theory, I'm solving for any possible network. Any possible network, okay? So now I'm the planner. I'm going to maximize this function and decide the effort for everybody. And I might compare with the Nash equilibrium. And you understand, it's going to be different. Why? Because imagine with a spillover model. When I make an effort, I don't take into account the fact I'm changing the norm of my neighbor. So the Y bar change. And this affects my neighbor positively. So I'm creating an externality. So it's not the first best. And I'm creating always a positive externality to this guy. Right? That's why you have to resource further. So the two models. So let's start with the conformist model. So now it's a bit more tricky. If the planner solves the problem, there's one more term here. What does it mean exactly? So the intuition is very simple. Okay. When, as a person, at Nash equilibrium, I'm going to decide how much effort I do. Okay? The thing is that, as I told you, when I increase my effort, the average effort of my neighbor change. The question is that, am I above or below the norm? Imagine I'm above the norm. My effort is above the norm. What I do is that when I start to increase my effort, it's good, because then the guy gets closer and closer to the social norm. So in that case, I'm creating positive externality. Now imagine I'm below the norm. So my effort is below the norm of my neighbor. I increase my effort, I told you it's good, but if I'm above the norm, when I increase my effort, they get further away, and then you have a negative externality. So depending if you're above or below the norm, you create positive or negative externality. This is this term. So this term is positive if my neighbor is above the norm, and is negative if it is below the norm. Is it clear, the intuition? So what I'm going to do, the first best, of course, you have this extra term, and I need to correct for this term. The spillover is different. There is this extra term from the planner, but it's always positive. So basically, everybody is putting too little effort compared to the first best. So the thing you're going to do, you want everybody to increase their effort, right? This is the term here, compared to Nash equilibrium. So I can calculate the first best in a simple way. Imagine I had one stage, which is the subsidy or tax stage, and the planner play the first game, and he say how much S or T I have to give, given that in the second stage people play Nash equilibrium. Okay? Standard one. And what you obtain is that in the conformist, this is how much subsidy you have to give to everybody. Of course, it depends on your position in the network, but you can see that it can be positive if this term is positive, or negative, as I told you before. And for the spillover, it's always positive. Is that clear? Let me give you an example to be sure we understand. So look at the simple example I can do. Think about the star network. By definition, the star is going to put the highest effort, right? So it's going to be always above the norm of the other people. Whereas the periphery is going to be below the star, it's going to be below. So what you want to do, which is very surprising, you want to tax the star and subsidize the periphery. Right? Remember, the norm of 1 is what? Is the average of 2 and 3. But the norm of 2 is 1, and the norm of 3 is 1. So 1 and 3, 2 and 3 will be always below the norm, which is 1. So I can calculate that. So Nash equilibrium, this is the value for some parameter. This is the norm, and the optimality is this one. So star put highest effort, and you want to switch from here to here. Well, what you do, you tax the star, and you subsidize the periphery. Obviously, because they create negative excitation. Now, if you do the same exercise for the spillover model, right? Well, you want to switch from Nash to optimal. You give subsidies to everybody, but different depending on the position of the network. Okay? So that's the idea. Now, well, I can do now what is nice, and I think that is I think for me the more exciting part of the paper is to show with the data counterfactual policy, where in one case you think it's a limb model and the planner tried to put subsidies, and the other case the real model are charged. So left-hand side, I'm just plotting the subsidies that restore the first best in, if it is conforming or spillover, it's not very important. This is a key figure. And this is a mistake that you're making. So remember, spillover, most active one. So if I am in a limb model, I'm going to give, in the spillover model, I'm going to give subsidies this way. So basically, when these guys do reduced form regression, they say, we need to subsidize every student on average so that people will be better off. What I show you is not true. What you should do is the following. This is the blue one. What does it mean? It's very strange. You give 0 subsidies to 80% of the student, and you put huge subsidy, you target the guy which has the top on the group. So basically, remember, only you care about the most active agent, right? And the maximum, remember, grade is 4. So basically, who you want to subsidize? Of course, I can subsidize a group of very smart kids. Let's say you have a group of people get 3.5, 3.8, 3.9. I can subsidize, but the effect is going to be very small because they're going to reach from 3.8 to 4. Now, the one I want to subsidize are the low kids and the top kids there. So imagine you have a group of 4 kids which have 1.4, 1.5, 1.6, 1.8. So what you want to do, you give 0 to these 3 kids, and you get the maximum subsidies to the 1.8. Because this can have a huge effort, and this is what I give you. I'm going to give subsidies to these top guys up to 3. So the maximum you can give. Why? Because all the kids which are in this group care about these guys, and the one, if he switch from 1.8 to 4, this kid is going to increase a lot because of the spillover model, right? Whereas most of the people, you don't care. I mean, the people who are not the most active one, you don't give anything. So basically, this shows you that if you really believe in the model and the estimation, you should target kids to have a first best, whereas the other model do a very bad job by just giving everybody the same subsidy. Okay? So we can do the same exercise. Oh, it's good, we are on time, no? 40, yeah, 5, yeah, 5, yeah. So you can do the same exercise for the, for the risky behavior. Remember, beta is less than 1, so you care about the less risky guy, and you are conformist, not spillover. It's different. So here's a policy. So in red, what you do is that you tax, remember, conformist, you need to tax some people. So you tax some people, but this is absurd. You give a lot of subsidies above 1. Why? Because the people who are very risky, and if you are in a group of risky people, you want to conform to them. So you need to subsidize them. But if you believe in my model, then no, it's not true. You should tax nearly everybody. Why? Because you want people to reduce their risky behavior, because that's what you care. You care about the less risky one, not the high risky one. So you want to give a lot of negative subsidies so people are less active, and subsidize very few people at a very low level. So it's a totally different application of the model. And I can do the same thing for self-esteem. This is again the difference. So in the limb model, you do that. Here, it's a spillover, so there's no tax, there's only subsidies. You give very little to a lot of people, but then you help a lot the people to increase their self-esteem. Okay? So you see, what I show you here is that if you don't know which model you estimate, and so you're making this extremely strong assumption and say, I'm going to only improve this identification, that's what people have been doing, not for 1 year, for 10, 15 years, and all these papers published in top 5 journal, they say, let's do Lee model, but we have to do a better job in identification. So what they do random allocation to roommates. They do RCT, and there's a lot of paper about that, and then they show that indeed the lambda is significant, and then they get some policy application. I tell you, you have no clue what you're doing, because you don't know which model is true. Is it the conformity spillover? And more importantly, you are making a huge assumption by assuming beta equal 1. Maybe these guys don't care about the average. You're imposing 1, maybe they don't care about that. Even it's significant, maybe they don't care. Maybe they care only about the top or the mean. You don't know that, and you need to test it. So, okay, it's good I'm in advance. It's not finished, I'm going to do some stuff here. So basically, the conclusion is that whenever you do policy, you have to be very careful to know which social norm matter. So I work a lot before doing network. I was doing urban economics, as Pascal was saying. And I was working a lot about how we can solve the problem of inner city African American. That was a huge problem in the US. And these guys have 2 problems. They live in geographically segregated area, as you know, very far away. But there's a second aspect, which is very important, of course, now, is they live in socially segregated area. What does it mean? It means that these guys don't find job. Why? Because all their friends are unemployed. So the people who are employed are white people from a different class. So they're never going to get, they're going to be stuck there forever. How are we going to improve that? Well, you know, sometimes you do policy, you say, oh, let's, I don't know, let's give money to some people. And then maybe some people leave the area and the area is worse. No, you have to identify who they care about. So all the policy of urban poverty should be targeted to urban area and to people that they care about. So for example, a local leader or someone who works and so forth. You need to change social norm. Again, in this area, I don't know if you know, but 80% of these kids don't have a father. They've never seen someone with a tie going to work. So how can you say you have to work? So how you change social norm? Well, you need to know. Do they care about the leader of the group, or do they care about average people? Would they care? That's the idea about this kind of thing. Now, 2 things I want to show you before I stop, and maybe you want to ask question. Do we need to have this? So to have this methodology, do we need to have network data? Actually, not. So I'm doing some paper on kind of macro paper. We have this Swedish data, which is we call it Försämring, which is like the parish level, which is quite high level. We don't have network data. So what we assume is that, well, basically, you can still estimate the same equation. The only difference now is that this parish or municipality data, you assume that you have a link if you live in the same area, municipality, and no link otherwise. So you can still estimate the same equation, but now it's not friendship, it's about geographical link. And you know, any space you want to know, social space will work. You don't have to have a direct friendship. You can have spatial space, political space, whatever you want, and you could test and see what matters. So what we did here, there's this lecture about consumption. And people assume that, well, when I want to consume something, I care about the average of my group. We don't know. You know, if it is conspicuous consumption, you care the guy who have a Porsche and you want to have a Rolls Royce, you know? So which part of the decision matter? So again, this question here, not about network, is about if I want to make a consumption decision by asset, which part of the decision matter? Is it the top guy in my group, or is it the average, or is it the one below? I don't know. Okay, and the last thing I want to show you, it's a recent paper that I'm doing on the UK data. Okay, sorry, yeah. Okay, so very quickly, sorry about that. This is this paper when we do that, and it's nice because the idea is to say network is about targeting, right? So in the UK, that's a real policy, they've done what they call the hotspot policy. So basically, they put all the police in area when you have a lot of crime. That's what we're going to do. Now, I'm using network data. So now network is when two areas are contiguous, GIG equal 1, right? So I'm looking at very detailed area, which is called the lower layer super area in London, and I'm looking at the network this way. And instead of targeting the area when you have a lot of crime, attacking the area when you have a lot of connection. So if this area, you target them, it will not spill over the crime, okay? So look what you get. This is what the police is doing, is in blue. This is London. And this is what you should do, which is the black one. And in yellow, you have the point where the two are the same. So very rarely, what they're doing is correct. So most of they're doing to reduce crime is not correct. And you can show that, and this is true mostly for property crime, not for violent crime. Basically, if they were doing our policy, and we're working with the police in the UK now, you could reduce crime by 11%. And the last thing I want to show you, which is crazy, is that we know how much money they spend every year in terms of hotspot, and we show by our estimation that they could save £255 million a year and have the same effect on crime by doing targeting on this area rather than the other one. So the conclusion now, and I think we can stop, the conclusion of that is that you need the model to understand the data, for sure. You know, a lot of people say, we have big data, now we don't care about model now. If you have huge data set, how are you going to know anything? You need to have a model to understand the intuition, and then address policy based on the model, and then if network matter, you should target. Okay, I think I will stop here, if you want.
So we have time, about 5 minutes time for questions.
Sure. No, it's fine to speak, yeah. Yeah, yeah. That's what, yeah. Basically, what we show is that we have this measure of interconnectivity. So basically, the idea is similar to Vasco. You say, if I remove this area from London, how much crime going to decrease? And so these areas are very important because they're very connected. So these are the areas that will spread mostly crime. So this area, if you put a lot of police, crime doesn't spread. Apparently, it was, I didn't check exactly, it was central London, and I don't know. But again, it depends which type of crime and which type of area. So this is for Manchester, is very different, as you can see. But for London, what we have is this one. So it was mostly this area. And what is interesting here is that when you talk to the police that target high crime area, which is a lot of high ethnic minority area, what we show actually is not the area you want to target. It's not when you have minority, and it's other area in terms of characteristics. I go quickly here, but that's the whole paper is about that, yeah. So, yeah, sorry, Sanjeev, behind you.
So I'm going to ask you your question. This is the question you asked Vasco.
Sure.
Earlier today. So, just looking at this, fascinating.
So you're all speaking about the last part, the small part of the paper, not the main paper, okay?
Well,
Yeah.
this is 250 million.
I know, no. Yeah, sure.
So, just going to you ask the question you asked him, which is, so I think it's sort of a high level question, which is the following: that when you have a policy, right, it's basically like a lupus critique question.
Sure.
We're assuming that the network is somehow invariant to the policy. Right?
Sure.
Whereas a network is a human creation. So when you target these people, presumably people will find ways around, right? So I guess you have to collect data regularly to update the policy. Is that?
Let me answer. In that case, this doesn't apply because the unit is not the people, is the district. So they don't, the district is not someone forming links. So the district is where you put the unit. So it's not human being here. It's not about removing a person from a network. Here is actually to remove a district from the area. So I'm targeting a district, and I say this district are generating a lot of spillover of crime, so just put the police there. And then we simulate how much crime is going to decrease.
So this is some kind of contiguity network.
Yeah, so it's not a social network.
But then people can move.
Sure, and that's why we're doing now in the follow-up of the paper, look at data about how people move and how when you do hotspot, because when you do hotspot, it's the same idea. Yeah, and so we're looking at that. Yeah.
Yves, can I?
Sure. Oh, sorry.
So I take, going back to the first part, I take what you said, right? So part of the message is you really want to think about who people care about or
Sure.
what is the peer that matters. But then econometrically that starts putting a lot of weight on you knowing the network, right? So if I think by introspection, not very scientifically, my trouble peer group was very different from my study group.
Sure, of course.
So, and then if you ask me, what is my network, name 10 friends, so what you would find is I would probably put someone there from the study group, and that person, because he's in the study group of the nerds, will probably appear as the beta is loads on the max, because
Sure.
there's the one guy that is actually getting good grades in that group.
Sure.
So kind of, to the extent that people have different networks for different activities, so it's a little bit of a kind of endogenous network, in this case it's across activities. There may be now, pushing, I understand what you're saying, pushing in that direction, so we start loading, kind of, it would be interesting to have some sort of understanding to what degree can I get biased responses of beta to network mismeasurement.
Sure. So, of course, the application here is not the point of the paper, it's a methodology paper. So I do that, and this particular network is, you have friend network, and then the activity are not related to network. Yeah. So there's two answers to that. First, you could do this exercise for each network, one for criminal network, if you have the information. Now there's a literature which I work on multiple activity, multiple networks, and you can apply the methodology. So imagine I have a friend in crime and friend education, and then there's theory paper.
That's
okay.
exactly where I was going.
Yeah, and I have a paper about that. Yeah, sure.
And assume, what kind of bias are people doing by assuming that there is one network?
Sure.
When the network itself is multiplex.
Sure.
So you could probably, maybe you can derive with closed form the size of the bias on the beta.
Yeah. And by the way, multi-layer network, at least from the theoretic point of view, it's very promising. There's a lot of paper in sociology. To my knowledge, there's no theoretical paper. And I have one or two now recently, and I'm working on that. But it's very promising if people work, both theoretically and empirically, for economists. There is some sociology, but there's very few papers about multi-layer network. Matt and Aru and all these guys have a new paper about that. Yeah, so thank you.
We have time for one more question. Go ahead.
Yes, so again, regarding endogenous networks, but you have longitudinal data. No?
No, it's only one point in time, but the endogenous of network doesn't matter here. It's not an applied paper. What I just show you is that beta is not equal to 1. You can correct for endogenous of the network. We did some work. It doesn't matter a lot. It's just to show you that beta is not 1 in the data. That's what we want to show.
So
but you can do, there is a literature on that, on the network. Yeah, sorry.
Theoretically, I was just wondering whether it's a spillover model or a conformist model that correlates with how the network is formed somehow.
Sure.
So if I thought that it was longitudinal data, then you could maybe test how the network is evolving and whether there is some correlation within it.
That's easy to do, but that's not the aim of this paper. Yeah, this paper is really about this point. Take the Lee model where the network is exogenous. Where is it coming from? Yeah. But that's a good point. We could do that. Yeah. Yeah.
Thank you, and thank you, Yves, once again.
Yeah. Maybe they want to say some closing word for the conference. Yeah.
Can I please request Professor Arunava to give a vote of thanks and give a formal end to the conference?
So I just
like to say a few words on behalf of the Econometric Society. I'm the chair of a committee which has the task of finding a venue for conferences in the CSW region, Central, South and West Asia region of the Econometric Society. It's actually the second conference that we've organized, the first one being at IIT Bombay and the second one here. So I'd like to thank particularly Abhijit and his colleagues at IIT Delhi. Done a wonderful job. We've probably eaten a little too much, but thank you again for agreeing to host this conference, and thanks to you and your colleagues and the student volunteers. Then I'd like to thank Sanjeev, old friend, for agreeing to be program chair. It was done rather hastily, and I hope it wasn't too stressful, but thank you again for the wonderful job you've done. Thanks to the keynote speakers. I hope you guys have taken the opportunity to take selfies in front of the posters which are all over the campus. And thank you to all the participants. I hope you've had an enjoyable time. So thank you very much.